Good morning everyone. Let us solve another problem on design of shaft. A shaft is mounted on a bearing 400 mm apart and carries at its midpoint a gear of 200 mm pitch diameter. The gear causes 8000 Newton radial load and 3000 Newton tangential load as shown. The shaft is rotating at 500 rpm. If the allowable shear stress for the shaft is 60 Newton per mm square, determine the diameter of shaft. So in this problem we are having a gear drive where a gear drive has two kinds of load, that is radial load F suffix R and tangential load, we call it as Ft. In this case we need not find the radial and tangential load as they have already mentioned in the diagram, and diagram is also given. In a diagram you can see there are two bearings A and B and a gear is placed exactly at the center, and since there is a gear rotating, direction of rotation is not shown, but they are given the radial force acting downwards and tangential force is acting from left to right when viewed from left side. So let us write the given data. Given length equals 400 mm, rpm 500, diameter of the gear is 200, so we will convert into radius 100, tangential stress 600, and the force Ft equals 8000, Fr equals 3000. So first we have to find the bending moment for Fr. So you have a bending downward loads. So what is the bending moment for downward loads? You have to calculate. Since the load is acting exactly at the center, so the maximum load will be at the center. So bending moment vertical will be Fr into L by 4, or we can say in general formula, if the load is acting at a simply supported beam at the center, then load will be maximum load will be at the center. So bending moment will be maximum at the center. So MB equals Fr L by 4. So substituting it, we get the answer 8 into 10 raised to 5 Newton per mm square. Now we will consider tangential load. When I consider in tangential load, in the sketch it is shown from left to right. Sign convention is if you are viewing the image from the front view, it will be the load will be acting towards you in your direction, right? Anything acting in your direction will be taken as negative. So since the load is exactly at the center, we are considering maximum bending moment is always at the center. So again substituting Ft into L by N. When going for a horizontal load, you have to neglect vertical load. When you are going for a vertical load, you have to neglect horizontal load. Substituting it, we get the answer 3 into 10 raised to 5 Newton per mm square. Now you have to calculate torque due to the force. Always remember in the gear, whenever the gear drive is there, torque is due to tangential load only, not due to radial load. In the design of gear drives, we will be going into detail about that. So as per the gear formula, the data book is available. Torque due to the force Ft is given by tangential force into radius of the gear. So this is the formula only for the gear. Substituting the, you'll get it 3 into 10 raised to 5 Newton per mm square. Now you have a vertical load, you have a horizontal load, so because of it we have to calculate resultant load. So resultant bending moment will be root of horizontal moment square plus vertical moment square. So we get it as 854.4 into 10 raised to 3 Newton per mm square. Now we have the torque answer, we have bending moment answer. So directly we will go for according to maximum shear stress theory, assuming that Cm equals 1.5 and Ct equals 1 and K equals for solid shaft is 0. Since they are not mentioned any detail about the shaft, we assume it as solid and we assume steady load. Since gear is there, always the load, most of them the load will be steady. So the general formula. Here we are neglected K value and directly substitute in the formula. D naught equals 16 by pi into 60. where 60 is sigma tau as per shear stress is tau, and 1.5 into 854 the values which are given and into second value. So we get the answer as 48.16 mm. So we will refer this answer to that handbook answer and finally get D in articles 50 mm, the standard diameter, from the page number 57 3.5. Thank you.